Our reality is riddled with mysteries. Everything we've ever seen, stars, galaxies, planets, even us, makes up just 5% of reality. The rest, hidden, unknown. We've spent centuries trying to understand, peeling back its layers, looking deeper and farther. But instead of finding simplicity at the center, we find inexplicable complexity. The strange gets stranger. The weird gets weirder. From the farthest reaches of the cosmos to the invisible subatomic world. Today we journey to the edge of human understanding, to face the mysteries that shape our reality.
Our first mystery is hiding in plain sight. Galaxies spin so fast they should fly apart, yet something invisible holds them together. It was first observed by Fritz Zwicky in 1933 at the Mount Wilson Observatory while studying the Coma Galaxy cluster. He noticed the galaxies were moving far too quickly, as if an unseen mass was holding them in place. It led us to believe that something is applying an effect that visible gravity alone cannot explain. That empty space is not empty at all, but filled with an unseen mass and energy. We call it dark matter, unseen, untouchable, and unknown. We now estimate that it makes up nearly a third of the cosmos. And still, after decades of searching, we have no idea what it really is.
And if that mystery wasn't strange enough, the universe holds an even deeper secret. One that isn't holding things together, but pulling everything apart.
While dark matter holds galaxies together, another force is doing the opposite, pushing the universe apart. Not only is space filled with hidden matter, it's being stretched by a hidden energy. This dark energy drives the universe to expand faster and faster. Its story begins with Einstein's cosmological constant, a term he introduced in 1917 to keep the universe static. Later, when the expansion of the universe was discovered, he called it his greatest blunder. But today, that same constant has returned as a possible explanation for why the expansion is accelerating, a mathematical fingerprint of the energy woven into empty space itself.
It dominates nearly 70% of reality, and yet it's a complete enigma. What is pushing the universe apart? A new force of nature, or a flaw in our understanding of gravity itself? And this accelerating expansion leads us to another profound puzzle, a disagreement in the universe's most essential measurement.
The story began in the 1920s when Edwin Hubble discovered that distant galaxies were moving away from us, and the farther they were, the faster they receded. This revealed something astonishing. The universe itself is expanding. From this came the Hubble constant, the rate at which the universe grows, a single number that should describe all of cosmic expansion.
But today, that number depends on how we measure the universe. When we study the early universe through the cosmic microwave background, we get a value of about 67.4 kilometers per second per megaparsec. But when we observe the modern universe using Cepheid variables and type 1 a supernovae, we get a much higher value, around 73 to 74 kilometers per second per megaparsec. A small numerical gap, but large enough to shake the foundations of cosmology. Two answers, both extremely precise, both correct within their methods, yet impossible to reconcile. This is the Hubble tension, and it challenges the very idea of dark energy and the cosmological constant. Maybe dark energy evolves over time. Maybe new physics is waiting to be discovered. Or perhaps our entire model of the universe needs to be rewritten. And if the expansion of the universe confuses us, the origin of the matter within it leads to an even deeper mystery. In 1928, Paul Dirac combined quantum mechanics with Einstein's relativity and discovered something unexpected in his equations. They predicted a mirror version of the electron, identical in every way, but with the opposite charge. This theoretical particle became known as the positron, the first hint of antimatter. Just a few years later, in 1932, Carl Anderson observed this position in cosmic rays, confirming Dirac's prediction. Antimatter mirrors the properties of matter, same mass, opposite charge. And when the two meet, they annihilate perfectly, converting into pure energy. And here's the problem. The Big Bang should have created equal amounts of matter and antimatter. If that were the case, they would have annihilated completely, leaving nothing but radiation. Yet here we are, a universe made entirely of matter. Some hidden asymmetry tilted the scales in our favor. Without it, no galaxies, no stars, no life could exist. To explain such profound imbalances, we turn to our most powerful theories, only to find that even they refuse to agree with each other. Quantum mechanics governs the very small. General relativity rules the very large. Each works beautifully in its own domain. Quantum mechanics defines the atomic world, how particles behave, interact, and even how your device is able to run this video. Gravity, on the other hand, shapes the motion of planets, stars, and galaxies. It defines the very geometry of space and time. But when we try to combine these two pillars of physics, the equations fall apart. Gravity simply doesn't work within the rules of quantum mechanics. For decades, physicists have tried to bridge this divide. One idea was string theory, the proposal that all particles are not points but tiny vibrating strings. In theory, these strings could unify all forces, including gravity. But string theory comes with problems. It requires extra dimensions we've never detected, predicts no single testable result, and offers a landscape of possible universes so vast that it struggles to describe ours uniquely. And so, the divide remains. A true theory of everything, a single framework to describe all of reality, is still the holy grail of physics. And nowhere does this conflict between our greatest theories become more violent than in the heart of a black hole. Black holes were first discovered, not in the sky, but in mathematics. A strange prediction that emerged from Einstein's equations of space-time. In 1916, while serving on the front lines of World War I, Karl Schwarzschild found a solution describing a region where gravity becomes so strong that nothing, not even light, can escape. Einstein himself doubted such objects could exist. But over the decades, evidence kept piling up. Stars whipping around invisible masses, gravitational waves from massive collisions. And finally, in 2019, the Event Horizon Telescope gave us the first ever image of a black hole. And yet, even with all this confirmation, black holes remain the most troubling objects in physics, because deep inside them lies a singularity, a point where density becomes infinite, and the fabric of space-time tears itself apart. Here, quantum mechanics and general relativity don't just disagree, they collapse together. So, do the laws of physics survive inside a black hole? Or do they break entirely? Some believe black holes may be the bridge we're looking for, the place where quantum mechanics and gravity finally meet. maybe even the key to understanding how the universe itself began. But the universe doesn't only break our laws on the largest scales, it behaves even stranger on the smallest ones. In quantum mechanics, particles exist in many states at once, until we measure them. The act of observation collapses possibility into certainty, or at least that's what we think happens. The famous double-slit experiment revealed this strange truth. Particles behave both like waves of probability and individual particles, forming interference patterns until we observe them and the pattern collapses. Schrödinger's wave equation describes this fluid, ghost-like reality mathematically, yet it cannot explain why measurement changes everything. And from this strange quantum behavior, Einstein uncovered a deeply unsettling implication. He realized that two particles could become linked in such a way that changing or observing the state of one would instantly affect the other, even across vast distances. He famously called it spooky action at a distance. This phenomenon is known as quantum entanglement, where two particles are connected in a way that measuring one immediately reveals the state of the other, as if somehow they are not truly separate at all, a connection that seems to defy the very fabric of space and time. Today, this very phenomenon is the foundation of quantum computers and ultra-secure quantum communication. But even with all this progress, the foundational mystery remains. Why does measurement collapse a wave of possibilities into a single, definite outcome? Does reality only take shape when observed? Or are we simply revealing what was already there? This is the quantum measurement problem, and it challenges the very nature of reality. And if understanding reality is difficult, understanding the one who observes it may be the greatest mystery of all. Beyond the universe and the quantum world lies the greatest mystery of all, one that lives within us. After all, it is because of consciousness that we can reflect on our existence, question the universe, do science, and try to understand the nature of reality itself. How does the brain, a network of neurons and electricity, give rise to thoughts, feelings, and the sense of I? This is the hard problem of consciousness. Physics can explain particles and forces, but not why we experience them, not why the universe feels alive from within. Is consciousness just an illusion created by matter? Or is it something fundamental, as basic as space, time, and energy itself? And when we step back from all these mysteries, from galaxies to particles to the mind itself, we are left with the deepest question of all. What does any of this mean? We live in a universe of unanswered questions. Every discovery leads to deeper mysteries. Perhaps we are only scratching the surface of a reality far stranger than we can imagine. And the more we learn, the more we realize how little we truly know. We know so much, yet so little. An intrinsic and undeniable truth. It seems from our perspective that reality may be infinitely complex. But what does that mean, if it truly is? Are we destined to journey endlessly into this infinite chasm of mystery? And until we do, how do we define the meaning of our reality and of existence itself? Can science, powerful as it is, truly give purpose to all that we observe, to all the mysteries and the wonder of creation around us? Can equations and experiments explain the very reason for existence or guide us toward meaning in our lives? Can science answer the greatest mystery of all? Why are we here?